When we're building networks using that hierarchical network model, one of those prevalent set of networking blocks we're going to use are going to be the access, distribution, and core layers. In fact, back in the day, that was pretty much all our networks consisted of. And so we had all these services just sort of hanging off of the core. Now it's that building block model that we've described, but the access and the distribution layer are still a very mission critical part of our networks. In this video, we're going to explore how exactly the access, distribution, core layer all relate to one another before diving into more specifics in subsequent videos. Let's dive in. If we had a small business and we needed to build out a network from scratch and we just have maybe 10 to 12 users we have to connect, we're probably going to start with a switch. We might even deploy redundancy and have a second switch. And we're going to connect our users to these switches and of course make sure that these switches are connected to each other for redundancy, or well, for connectivity as well. And from there, we'll have maybe an internet router hanging off of here. Maybe this is a firewall as well, pointing out to the internet, connecting in at these two different switches. We don't really need a whole lot more than this if we only have 12 users. But think about it as we scale this out. Let's say we have more users that we now need to connect, and they're off in a different part of the building. Well, now we need to connect another switch. And so that switch is going to connect in. Well, how are we going to connect these switches together? I mean, we could connect one-to-one like this, and that's great, other than that's a single point of failure. And we already said we want to avoid single points of failure in our network designs. And so we're going to connect this switch to both of those switches, relying on spanning tree to handle the loop prevention. But then we have another set of users coming online because our business is good and we're growing. So we have a bunch of users over here, and now we need to connect this into the network. How are we going to connect this switch to these other three switches? Well, following our earlier logic, we can do a full mesh of connectivity and bring this into all of the switches. This is going to create a spanning tree nightmare, but hey, in theory, it's going to work. Might be a little tough to troubleshoot, but it will work. But what we see here is we're deploying a full mesh of connectivity among all of these different devices. And the primary reason we're doing this is from a redundancy perspective. And as we can see, this is not going to scale out as we deploy more switches. Imagine if I have now 20 or 30 switches in the environment. I can't full mesh all of these switches together, and without an intentional network architecture, I'm going to end up with switches hanging off of other switches, maybe a whole line of daisy chain switches. Maybe this switch on the end connects back to that switch on the left, and so we can see that this is just not going to go well for us if we continue to scale out organically without a plan. This is where the enterprise campus architecture comes into play. We have an access block. This access block is going to consist of a lot of switches. We could have 2 switches, we could have 20 switches, we could have 100 switches inside this access block. And remember, in the last video, we said in a lot of cases, we're only going to have 2 switches in a network block, or maybe 2 routers, but the access layer is definitely different. We can have a lot of different switches inside of this network block. So that's great from a logical perspective that we have an access layer block, but let's draw this out on the right as having a lot of different access switches. Let's just draw 6 switches on here. And we know that we don't want to connect all of these switches to each other, at least not like we did in the last drawing. So the idea here is that we can deploy a pair of switches, and these switches will be called distribution switches. We're going to connect these distribution switches to each other, and we're going to connect all of the different access layer switches. So down here, the access layer, they're going to connect into this distribution layer. So there's the switch on the left here. We're going to connect this up to one of the distribution switches. But again, as we just discussed, we want redundancy. And so we're going to connect this up to the second distribution switch as well. Next, I'll repeat this design for the second access layer switch. I'll connect it up to both distribution switches. And so on and so forth. I'll do this for all of these access layer switches in my environment. Now we can already get a sense that this is a much better scaling methodology than what we had in the previous drawing. It's no longer full mesh, even though technically speaking, I could connect access switch 1 on the left to access switch 2, 3, 4, and spanning tree should handle all of these loops fine, and so in theory, I'm just increasing my resiliency. But this is going to cause a lot of problems from a troubleshooting perspective. It's going to open my network up to additional failure domains, because a spanning tree does have a hiccup somewhere, and it's going to cause a whole lot of issues. So instead, we do not connect the access layer switches to each other, except in one particular case. And that would be, what if these access switches are all part of different physical locations? Maybe we have several different access closets here that I'll just draw in pink. So let's say I have closet 1 here on the left, and I have 3 different access layer switches that are connecting to users. How do I connect these individual switches into the network? Now, if I adhere strictly to this model, I would connect each one of these switches up to the 2 different distribution switches. And there's nothing preventing me from doing that. In fact, that arguably is the best architecture from a network logic perspective. However, we know that that's not practical as much as anything, because in a lot of cases, these are going to be fiber runs in the building. And I don't necessarily have 12 different pairs of fiber to connect up all of the access switches in my closet. And so we have 2 main options for dealing with this situation. First up is to create a network loop among the switches inside that access layer closet. Now we have direct connections from the distribution layer to a head-end access switch, switch 1 in this case, and then we have a loop behind switch 1. But another option would be to deploy those switches behind switch 1, but instead of looping through switch 1 locally, we loop through the distribution switch. So we'd actually disconnect this line here and bring the distribution connection down to the bottom switch. Now we have a loop through the distribution layer rather than a loop through the head-end access switch. In fact, at this point, there is no head-end access switch. Now we do have some better technology these days that can help us deal with this situation. And specifically, we'd be looking at chassis switches as well as stackable switches. So let's say in closet 3 here, we have deployed 5 different switches, but we've stacked them together into one logical switch. Well, at this point, we don't need to worry about looping anything because we're just going to link this stackable switch up to the 2 different distribution switches, and then we've achieved our architecture. So looking back on the left to our network building block perspective, now we have a distribution block that's connecting in logically to the access layer block. Now we're going to be going into more detail on what exactly we expect out of distribution switches, and for that matter, what we expect out of access layer switches as well. We're going to be covering that in more detail throughout the course of this skill, but for now what we need to understand is how the access layer block is connecting to the distribution layer block. Now if this is the extent of my network, then I don't actually need to deploy anything else. I can bring my network services and the internet into the distribution layer, but what if I have a different situation? What if I have a lot of different distribution layers? So let's say this is one distribution block, this is another distribution block. Each one of these distribution blocks might represent a different building on my campus or between multiple sites. And what I'd expect here is that each individual distribution block is connecting to its own access block. And the question becomes, how do I connect these distribution blocks to one another? Because I could do a full mesh of connectivity. Maybe I only have 3 different distribution blocks, 3 different buildings on my campus. But think about that from a connectivity perspective, because I actually have 2 different switches in each one of these blocks. So if I want to connect them at full mesh, I'd be looking at something like this. Now technically this is doable, and technically it would work, but as we see here, this is going to introduce a lot of complexity, and it may require more fiber runs, for example, than we have available to us. So given the problems with even connecting up to 3 distribution blocks to one another, and considering how much more complicated it's going to be if we have more than 3, we want to create a new level of hierarchy, and that would be a true core layer. This core layer is going to be a pair of switches, ideally, that are focused on fast layer 3 communications. We're going to connect each individual distribution switch up to the 2 different core switches. This should look familiar because it's going to be the same type of architecture that we used to connect our access layer switches to the distribution block. The primary difference is that while this is a layer 2 connection in most cases between access layer and distribution layer, this is going to be layer 3 in all cases. We want the core block to connect at layer 3 from a scalability perspective. Because as we've discussed many times, spanning tree doesn't do the best job of scaling, and so since we need that at layer 2, we'd rather build our networks on layer 3. As such, this rounds out our architecture. We have an access layer block that connects up to a distribution layer block. We have a distribution block that's going to connect up to a core block. As we discussed in the last video, we can have multiple distribution blocks hanging off of this one core. Now, in a lot of cases, we might find that we need to collapse that core block into a distribution block somewhere, and that's fine. We always need to make sure that we're designing the network according to the needs. And if we have, for example, 100 users in our environment, well, we probably don't need a true core layer. We're going to be talking more about how we collapse 2 layers together, in this case maybe collapsing the core block into the distribution block, later on in this skill. So when we're designing campus networks, we want to make sure that we take this enterprise campus architecture into account. The architecture consists of 3 main blocks. We have the access block, the distribution block, and the core block. When we're connecting our access layer switches into the network, we're going to connect that via distribution layer, so an access block connects to a distribution block, and a lot of times that will be at layer 2, but sometimes it might be at layer 3. Now in the same way, when we scale out and we find we have multiple distribution blocks, those are going to need to connect up into the core block. The core block is sort of the top of the pyramid from our hierarchical perspective. And that makes it so that we can scale out our network to as many access blocks, as many distribution blocks as we need. I hope this has been informative for you. I'd like to thank you for viewing. As a network engineer, if you needed to chop down a tree, which layer would you use to help you accomplish that? And that would be the axes layer. So you get the access layer. So in this video, we're going to be talking about the access layer and all of the parameters and properties that are associated with it. Let's dive in. When we think about the access layer and the switches that we're going to deploy, what kinds of things do we think about? Well, the access layer switch is going to connect us to users. We use that as an example a lot. But when we're talking about these users, this could be a lot of different devices. We have to think through all of the different variety of devices that might be connecting to our networks and the needs that those devices create. For example, not just PCs and laptops, but also phones. What kinds of services do we need to support voice over IP? On top of phones, we have video conferencing units. And when we think about video, we also think of cameras, so security cameras and such. On top of that, it's not just user devices that are connecting to the access layer switches. We also have network devices such as wireless access points. And one of the first technologies we think about that we need at the access layer to support half of these devices, such as phones and video devices and cameras and wireless access points. In order to support all of that, we need a technology called Power over Ethernet. We're going to be going into more detail on Power over Ethernet later on in this course, but for the time being, we need to know that Power over Ethernet is how we deliver power to these devices. Because in a lot of cases, it's difficult to connect a device both to the network and to the wall outlet. Especially when you think about access points in the ceiling, we don't want to have to run power connectors to the access points. Let's instead run power through the Ethernet line that connects back to our access layer switch. When we're speccing out our access layer switches, we not only need to make sure that it supports Power over Ethernet, but also that it can provide the Power over Ethernet budget that's required by our devices. For example, do we just have a few phones on the access switch, or do we have full-fledged video conferencing units and Wave 6 access points and all these devices that are very power hungry? In those cases, we might need a beefier power budget in order to support all of those devices at once. Now furthermore, as traffic comes into the access layer, we are going to be doing some identification and classification of that traffic. For example, we're going to assign a VLAN tag on ingress to the network. We are also going to apply QoS tagging to the traffic once it shows up at our access switches. We might use 802.1x authentication, or furthermore, use port security. That would be a layer 2 security mechanism that we can use to identify clients based on MAC address. And this right here is going to determine whether they have access to our environment. And that part makes sense, right? I mean, it's the access layer. It's how all of these devices are gaining access to the network. And so if we have a device that's attaching to the network that we don't want to be on our network, well, we want to deny that client access. Now at the access layer, we desire high availability to make sure all of our devices can stay online. However, because most of our devices are only going to attach via a single wire, there's not much we can do by deploying a second access layer switch to achieve high redundancy. Well, there's not much we can do to improve high availability by deploying a second access switch. Instead, as mentioned in the last video, we're ideally going to have a pair of distribution switches upstream, and we achieve high availability by linking up to the two different switches. Now that said, there are a couple other considerations from a high availability perspective. First of all, as we just said, make sure that our links upstream are redundant. But second of all, if we have a chassis switch, make sure we have redundant supervisor blades inside that switch. And third, we should consider deploying multiple access layer switches into a single closet. And that's not so much because we're going to have users connecting up to two different access layer switches at once, but instead, we could have some of the users connecting to one switch, we could have some of the users connecting to another switch, so if we do have a problem with one switch, it doesn't take down all of our users at once. Instead, half of our users would stay up at that point in time. Now that's most of what we need to consider at the access layer. However, there are a few other parameters that we might want to consider setting. First of all, we can configure storm control at the access layer. Storm control helps dampen broadcast storms, so as traffic is coming into the access layer switch, we limit the amount of traffic that we allow onto the network. Second of all, there's just general QoS rate limiting. For the most part, this will be performed on uplinks where we will only allow certain amounts of traffic depending on the QoS tags. This is because we have this concept of oversubscription, which means that we might have 48 users down here at 1 gig connections, that's 48 gig, and then upstream we only have 1 gig uplinks. And that's pretty normal from a networking perspective. We're not going to see a lot of clients taking full advantage of the 1 gig, but on the off chance that we do exceed the amount of bandwidth that we have on an uplink, we want to make sure that we're dropping the appropriate traffic. In other words, we don't want to drop voice traffic and video traffic and security camera traffic. We'd really rather drop internet surfing traffic if we can. On top of that, we have security parameters that we can configure, such as dynamic ARP inspection and VLAN access control lists, or VACLs. So ultimately, when we're looking at the access layer, we need to make sure that we're doing everything we can to get our users and our devices securely and redundantly attached to the network. So as the name implies, the access layer is all about granting access to our edge devices, whatever those are. In some cases, it might be a wired device like a PC, but then it might also be something that requires power, like a phone or an access point. So we got to think about PoE as being part of our access layer switch procurement. Second of all, when we are ingressing traffic onto the network, that's when we want to classify it. Now, from a classification perspective, we think of VLAN tags, QoS tags, and in some cases, we might use port security to identify that client and whether we want to grant access to the network. Third, from a high availability perspective, we're looking at having multiple links upstream, and then in some cases, we might want to deploy a chassis switch. And if we do that, we'd want to deploy multiple supervisors for redundancy if we can. And second of all, in a lot of cases, we might want 2 access layer switches at a minimum in a closet. That way we're not going to lose all of our clients in an access closet if one switch goes down. Last but not least, we have these other services that we can consider, things like storm control, rate limiting, and other security mechanisms that will keep our network safe. I hope this has been informative for you. I'd like to thank you for viewing. Sitting upstream of the access layer is the distribution layer. It sits in between the access and core layers, and in this video we're going to explore exactly what the distribution layer is doing for us and why we bother to have this middleman layer between access and core. Let's dive in. Now that we have an access layer and all of our users are connecting in via that access layer, we're going to find ourselves with a whole lot of these switches, and I've drawn 6 on the screen here, but we could have dozens of switches in the access layer. And all of those switches have to connect to something in our network, and that is going to be the distribution layer. The primary goal of the distribution layer is to aggregate physically all of the different access layer connections that are in our network. For the sake of redundancy, we are going to deploy 2 switches, and these switches have to have enough ports on them in order to support all of these connections. So if we think about it, if we have 6 access layer switches and they're all connecting into switch 1, but then for redundancy, again, we're connecting them all into switch 2, well, each one of the switches in our example here have 6 connections downstream to the access layer. That means if we have n number of switches in our access layer, then we need to have at least n number of ports on each distribution layer switch. Now this number could change depending on whether we want to further increase our resiliency or at least increase our bandwidth by deploying ether channels to the upstream devices. In that case, we would need more than n ports on each distribution switch. And by the way, this calculation is only for downstream connections. We still need some ports for upstream connections to the core layer, as well as connecting to the other distribution switch. Now a couple of things about the distribution layer. We can deploy the distribution layer at layer 2 or layer 3. And really what we're talking about when we say layer 2 or layer 3 are these connections down here. Are we routing down to the access layer? Are these routed connections, layer 3 in other words? Or are we running VLANs up and down these links? In that case, it would be layer 2 connections. We'd be running spanning tree and such. In most real-world scenarios, our access layer is going to connect in at layer 2, but we'll be talking more about the advantages and disadvantages to layer 2 versus layer 3 later on in this course. Now we recall that as traffic is entering into the access layer, it is going to get tagged with a QoS value. And we need to make sure that we are enforcing that QoS policy at the distribution layer. Now we also need to support redundancy, and that can be supported a couple of different ways. First of all, we absolutely want to make sure that we deploy 2 distribution layer switches. And you might say, well, Jeff, if it's so important, why would we deploy 3 or 4 distribution layer switches? And we'll see why here in a little bit when we're talking about layer 2 designs. But ultimately, we get a diminishing rate of return on our investment by deploying that many distribution layer switches. Furthermore, we can increase redundancy by deploying chassis switches. If we deploy chassis switches, we want to make sure that we have redundant supervisors. And potentially, we can deploy stackable switches into the distribution layer as well. Now, the conversation starts to change a little bit depending on whether this is a layer 2 or a layer 3 distribution layer. If it's a layer 2 distribution layer, then we're going to find that we have our SVIs, our switch virtual interfaces, located on the distribution layer switches. These are what we'd call VLAN interfaces. I always like to represent them as dots inside the switch because they are layer 3 interfaces, but they exist inside the logical switch configuration rather than being assigned to a physical switch port. If we're running SVIs on the distribution layer, then we need to be concerned about those first hop redundancy protocols that we spent so much time talking about earlier on in this course. And on top of that, because it's layer 2, we also need to worry about the spanning tree route. And we need to make sure that we align the FHRP master or active with the STP route. If, for example, we assign the FHRP active and the STP route to the switch on the right, well, what that should mean for switch 1 down here in the access layer is that the link on the left is going to be placed into a spanning tree protocol blocked state. That means that as traffic comes into switch 1, it will have no choice but to forward that upstream out its right interface. And that means it will land directly on the FHRP active rather than taking an indirect path to get to it. Incidentally, I mentioned earlier that we should really only deploy 2 switches to the distribution layer. This is one of those reasons, because FHRPs only give us an active and a standby state, and therefore we really only need 2 switches from an FHRP perspective. It gets complicated if we try to add a 3rd node. And it gets further complicated by spanning tree if we have 3 different distribution switches. As such, 2 distribution switches should be plenty for us. Now, if we're running SVIs on the distribution layer, then we are also going to be inclined to deploy access lists to those SVIs. So ACL enforcement is going to be a big part of the distribution layer's responsibilities. In the security world, we love to block traffic as close to the source as possible because if a bad packet arrives on a switch, well, I mean, if I let that packet go further into my network, then that just increases my risk. But the reality is that even though I'd love to cut it off at the access layer, maintaining access lists on every single access layer port in my environment just doesn't scale. And this is why we deploy access control lists to the SVIs, because that scales a whole lot better, even though that means that the packet now has to get up to the distribution layer before it gets dropped. Incidentally, by the way, this is not an ideal situation. It's just sort of how we have to deal with traditional networking, but we do have new ways of dealing with this with software-defined networking. And specifically, Cisco software-defined access is going to help us with this, and we'll be talking about SDA later on in this course, because Cisco wants us to know how do we design software-defined access as part of the ENSLD. Now, in most cases, the distribution layer isn't the final destination for packets. In fact, we want to forward those upstream to something, and that would be our core layer. Now, because these will be routed layer 3 links, we're going to be running a routing protocol with the core, and we have to advertise all of these SVIs to the core so it knows where these subnets live. But as part of that, we are absolutely going to want to consider route summarization as part of that configuration. Route summarization is going to take a bunch of subnets and aggregate it, ideally, into maybe one or two, a few different supernets. This is where the world of subnetting shows back up in our design principles. We want to make sure that we are aggregating our subnets together in such a way that we can summarize them and send less routes upstream. So if we design our subnets right, our core layer should only receive the summarized versions of those routes. Now, all that to say, what happens if we actually deploy layer 3 to the access layer? How does all of this change? And the only thing that really changes is that all of the layer 2 components that we talked about, the SVIs, the FHRPs, the spanning tree routes, the route summarization, all of that is now moved down into the access layer. And the reason for that is because now our users are connecting into, let's say, switch 2 here. Well, because these are layer 3 links, we'll draw these as dots again, representing layer 3 physical links up to the distribution layer. Well, now those VLAN interfaces have to live inside of switch 2, or the access layer switch of choice. And because the SVIs are down there, that's where ACL enforcement is going to happen. It's where FHRPs will live if we have multiple switches in an access closet, and so on and so forth. So in the end, we not only need to know what all of the services for the distribution layer are, but we also need to know which of those services will be offloaded to the access layer if we deploy layer 3 down to the edge. So when we think about the distribution layer, the primary purpose that we're deploying it is to aggregate physically the different connections that are coming in from the edge, from those access layer switches. Now, if those switches are configured for layer 2, we're going to find that the SVIs, those switch virtual interfaces, the VLAN interfaces, are deployed to the distribution layer, which means that we need to configure the FHRPs and spanning tree routes and align the two accordingly. Next, it's enforcing security policy at those SVIs via the access control lists. It's enforcing QoS policies, and we want to think about route summarization up to the core as well. And lastly, if we do deploy the access layer at layer 3, then we're going to offload some of those services down to the edge, and we need to know which of those services would apply. Basically, anything that's tied to the SVIs is going to be moved down to the edge. I hope this has been informative for you. I'd like to thank you for viewing. We have finally arrived at the core of the matter, and that would be the core layer. Now, I don't know about you, but when I was a junior network engineer, I sure thought that the core layer was going to be the biggest, baddest, most feature-rich switch on the entire network. But the reality is that the core switches are supposed to be built a little bit differently than what I had envisioned when I was young. In this video, we're going to explore exactly what those core switches are supposed to look like, as well as what the responsibility of the core layer really is. Let's take a look. Here's a picture of Cisco's Catalyst 9500 core switch taken from their website. These switches are designed to be in the core layer, and you might take a look at this and not be that impressed, because it's a single rack unit and it doesn't have a ton of ports on it. And as mentioned in the intro, when I used to think of a core switch, I thought about features, right? Like, we would just want as many features in the network core as possible. But here's the reality. There is only one feature we need on the core switch, and that would be fast switching. The reality is that we don't want to bog the core switch down with anything other than the ability to switch as fast as possible. So we think about enforcing security policies with ACLs. Well, we're not going to want to do that on the core switch, because that will slow things down and prevent us from switching as fast as possible. So regarding security, we're going to rely on other parts of the network to enforce that security policy, and we just mentioned that the distribution layer is responsible for enforcing security. We can deploy QoS to the core, but in most cases it's not going to be required, because we're going to be talking about much higher bandwidth links, and typically we don't need quality of service on those fat bandwidth pipes. So ideally, we don't actually deploy QoS enforcement on the core either, even though it's certainly within the realm of possibilities that we would want to do that. The reason for this emphasis on fast switching is because when we look at the network block diagram that we've drawn out, the core network block is in the middle of the entire network. Everything is coming through the core block. And so if we have two different distribution layers trying to communicate with one another, well, they need to get up to the core, and the core needs to take that packet in, figure out as fast as possible where to send it, and send it right back out. As we've mentioned, we already have enforcement of policy downstream of the distribution layer. So as packets come into the distribution layer, we enforce security policy, and in some cases quality of service and such, to the point that when we hand that packet up to the core, all we really want the core to do is to get it to the next hop towards its final destination. So here's what we really need to focus on when we're designing our core layer. First of all, redundancy. We want to make sure that we have 2 switches in the core layer and that they're connected at layer 3. Because they're at layer 3, that's going to give us the most scalability for our overall network. We don't want to be stretching VLANs and subnets among some of the other blocks in our network. Second of all, we're going to think about port count. We have a lot of different network locations over here, so maybe location A, B, C, etc. And even though I've drawn this as if each location has 1 connection, the reality is that we're going to have up to 4 and maybe even more connections coming in. So we have to make sure that we can support all of those different connections at the core layer. Furthermore, it's not just the port count, but it's also the port type. Are these copper connections? Are they fiber? In a lot of cases, they're going to be fiber because most of our network locations, let's say location C here, is a different building somewhere. That's usually not going to be within the 100 meters that Ethernet copper is able to get us. And so we can expect a lot of fiber ports, and furthermore, we have to think about the port speeds. We live in a world where 10 gig might be the slowest speed we should expect on a core layer. We might expect to see 40 gig and even 100 gig connections on our core switches. And when it comes to all of these, the port count, the port type, and the port speed, we need to be thinking about the future as well. We want to future-proof the design of these core switches to make sure that we can adapt to whatever changes come our way. So if our management comes to us and says, hey, we're about to spin up a new location, location D, then that doesn't mean that we have to upgrade the core switches just to handle that new connection. Now, in order to best future-proof us, we might want to consider a few things. First of all, we could consider deploying a chassis switch. Chassis switches come with the ability for us to expand port counts in the future if needed. So we don't have to know for sure what port count and what port type and even what port speed that we're going to need in the future. We can leave some of our chassis slots available for future expansion if needed. As always, if we deploy a chassis switch, we're going to want to make sure that we deploy dual supervisors for redundancy. When we think about core chassis switches, we usually think about the Catalyst 9600s. The 9600s are the spiritual successor to the 6500s and 6800s in the old Catalyst line. And when it comes to core switches, Cisco considers the Catalyst 9500 and the 9600 to be viable core switch types. So even though we might think about deploying stackable switches into the core, which in a lot of cases might work pretty well, Cisco doesn't strictly speaking make stackable switches that were designed for the core. For example, if we were to deploy on 9300s, the 9300s are stackable, and for smaller core environments, we might actually get away just fine with the 9300s. But Cisco doesn't consider the 9300s to be core switches, and it's usually best if we stick with the intended purpose behind a switch's design. So when it comes to the core of our network, it is not about features, it is all about speed. If we're going to deploy any feature to the core of our network that might risk slowing down our ability to switch packets, we need to really decide whether that feature is required and if we can't just push it out to somewhere else in the network. So from a design perspective, when it comes to our core switches, we need to make sure that we're considering the port count, the port type, and the port speeds. And we want to future-proof ourselves. So maybe deploying a chassis switch makes sense from that perspective, or otherwise making sure that we deploy a switch that's going to keep us flexible. Lastly, when it comes to redundancy, we always want to deploy 2 core switches. If they are chassis switches, then they should have redundant SUPs as well. And core layer should always be connected at layer 3. That improves the resiliency. We don't want to stretch subnets, extend broadcast domains, and extend our failure domain by doing that. Instead, we deploy layer 3 everywhere. That improves the scalability and really helps the core layer do what it was designed to do. I hope this has been informative for you. I'd like to thank you for viewing. Up until now, we have assumed that every network block that we've drawn in our diagrams consists of its own set of hardware. But what happens if we were to take one set of hardware and put 2 different network blocks on that same set of hardware? This concept is called collapsing. We've heard of collapsed core networks, for example. It's taking a 3-tier design and turning it into a 2-tier design. But the reality is that we can collapse a whole lot of different layers. It doesn't just have to be the core layer. In this video, we're going to explore exactly how collapsing different blocks in the network can work out for us in our designs. Let's dive in. When we say collapsing in the networking world, what we're really talking about is merging 2 different sets of responsibilities. For example, the responsibilities of the access layer with the responsibilities of the distribution layer. Or possibly the responsibilities of the core layer with the responsibilities of the distribution layer. Now in the latter case, this is what we call a collapsed core design. And it looks like this. Traditionally, we have our core block, our distribution block, and our access block. But rather than deploying 3 separate distinct network blocks, we're going to merge our core block into our distribution layer. What this means is that we will have a single pair of switches that are responsible for not only the distribution layer configurations and protocols, but also the core. Now we recall with the core block that we are going to be locked into fast switching. That's what we want to do, is to be able to very quickly take packets in and get those packets sent out. Meanwhile, the distribution layer is going to be concerned with things like first hop redundancy protocols and spanning tree route, as well as enforcing security policy. So the way this is going to work is we're going to have access layer switches coming into this collapsed core layer, And then on top of that, we're going to have other networking blocks out there that are attaching into this block as well. This might be additional distribution switches out on the network. This might be the internet block. It could be that network services block. It could be a data center. Regardless of what we have hanging out there, it's all going to come into these switches that are responsible for, yes, switching among all of the network blocks, but also responsible for connecting into the access layer, as well as all the protocols that we already identified. Now, the advantage to this design is that we don't have to purchase dedicated switches to serve as our network core. Instead, we rely on switches that maybe we already own, or otherwise the switches that we're procuring for our distribution layer. Unfortunately, it doesn't come without its downsides. For example, we've said that the core layer should be focused on fast layer 3 switching, but now our switches are split in their attention because we are also managing FHRPs and enforcing access control lists for our security framework. And so a big part of the question of whether I should collapse my core or not has to do with how many of these different network blocks there are. Because if I have a lot of different network locations and I need to be fast switching among all of them, well, it probably makes sense to have a dedicated core block. However, what if I don't have a dedicated internet block? And what if I don't have a dedicated network services block? And I really just have one distribution layer and one data center hanging off of there. So there's two different network blocks that are hanging off of what could be a collapsed core environment. For a network of this size, having a dedicated core might not make up the cost of procuring those network switches. In those cases, it makes a lot of sense to deploy what we call a two-tier design, because now instead of 3 tiers, a core, distribution, and access, instead we only have these 2 tiers here. We have the access layer and the collapsed distribution core. However, one interesting thing to note here is that if we do have another distribution layer that we're hanging off of this collapsed design, and that distribution block has an access layer block that's hanging off of it, well, the funny thing is even though we have a collapsed core design, we actually still have a 3-tier model for this particular location, because we have an access layer, a distribution layer, and what we'd consider to be a core layer. So we have to be a little bit careful with our terminology because yes, it is a 2-tier design for this location right here, 1, 2. However, for other locations, it's still a 3-tier architecture. Furthermore, as we've already mentioned, the core and distribution layers aren't the only 2 layers that we can collapse together. We mentioned the access and distribution layer. Let's say we have a true core layer with a bunch of different locations hanging off of it, but then we have a small location, a site with maybe 15 users. Does it make sense to have a dedicated distribution layer in a site like that? Definitely not. So instead, we would collapse the distribution and access layer together, probably deploying a layer 3 switch that can route back to the core, but then also we're going to connect our users directly to that switch. So that is absolutely a valid design for a small site, but what if we take that a step further? What if we have a very small organization? A business with maybe 40, 50, 100 employees, something like that. It might make the most sense to collapse all 3 together. What if we had the core, distribution, and access blocks all tied together on a single pair of switches? Does that make sense? Is that a logical thing to do? And the answer is yes, this is absolutely a valid design. We could have a pair of chassis switches, for example, that have connected to it not only the users, that would be the access layer component, but then we also have the SVIs here, that would be the distribution layer component. But then we're also going to have potentially a pair of data center switches, or maybe we have a couple of servers hanging directly off of those switches as well. So at this point, we're switching among our different network blocks, which means that it's the core layer as well. But here's what we need to keep in mind. Despite the fact that this is a small organization with just 2 network switches to speak of, this network design still embodies what we're trying to accomplish with this 3-tier architecture. We have access layer services, we have distribution layer services, and yes, we do still have the ability to switch among different network switches, so we do have core functionality in there as well. We want to keep in mind that this architecture was built to scale. And yes, in a lot of cases, that means that we're going to scale up to large enterprises. But in other cases, that might mean that we're going to scale down to very small locations. And so we have the flexibility to collapse or break out these network blocks depending on the needs of the network. So to recap, when we're talking about collapsing in the network, what we're really saying is taking the responsibilities of disparate network blocks and merging them together on a single set of hardware. So when we think about some examples like that, we think about collapsing the core into the distribution block. And we might want to think about that is when we don't have a lot of different network locations, we just maybe have a few. Well, at that point, it might not make sense to have a dedicated core. Next, we think about a small site. A small site doesn't necessarily need dedicated distribution switches, so we could collapse the access layer responsibilities, in other words, connecting users into the set of switches that's performing the distribution layer set of responsibilities. And lastly, for small organizations, why not collapse them all together, right? We could put the distribution core and access layer services all together on a single set of switches. Remember, this architecture is designed to scale both up and down. We need to be able to design a network that meets the needs of the organization. I hope this has been informative for you. I'd like to thank you for viewing. We have reached the end of another skill, and that means it's time to review what we've learned by taking a quiz. First up, out of 5 questions, which network block is responsible for connecting to the data center access switches? We didn't spend a whole lot of time on this, but it is important that we understand it. The answer here is D, aggregation. In a traditional campus architecture, we would have a core, distribution, and access layer. And we're mostly familiar with this as a 3-tier architecture. And what we need to understand is that on a data center side, we have a very similar architecture with a layer connecting to the access layer down here. But instead of calling this a distribution layer, we call this the aggregation block. So let's make sure that we know all of the different network blocks that we have available to us in our network designs. Question 2. Which of these services are associated with the access layer? Choose all that apply. When we think about the access layer, we are thinking about the fact that our clients are sending traffic into the network. This is the ingress point for the entire network. So for example, this is where we're going to do QoS tagging. We're going to tag that traffic with the appropriate QoS value that will tell the rest of the network how to treat that traffic. We're not concerned with fast layer 3 switching or FHRPs at the access layer. And because of scaling limitations, we don't want to do ACL enforcement at the access layer edge as well. Now, Power over Ethernet is absolutely going to be part of our access layer. We have a lot of different device types these days that require receiving PoE from the connected switch. And lastly, route summarization is not part of the access layer. So in this case, A and E are our answers. Question 3. This question's a little familiar. Which of these services are associated with the distribution layer? Check all that apply. Well, as we just said, QoS tagging is part of the access layer. That's not part of our distribution layer responsibilities. Fast layer 3 switching, we do layer 3 switching at the distribution layer, but our focus isn't on quickly switching among network locations, so B is out. Now, because we have our VLAN interfaces on the distribution layer, we can expect that our FHRPs are going to be there, as well as the fact that we're going to enforce access lists, again, usually on those VLAN interfaces. Now, Power over Ethernet is focused on delivering power to edge devices, and so that's not part of the distribution layer. And finally, route summarization. Route summarization is going to be part of the distribution layer, and here's why. We recall that when we have the distribution layer switches, we have all kinds of SVIs attached with this, and in some large networks, we might have dozens of subnets attached to these distribution switches. Now, we can certainly advertise dozens of subnets up to the core layer. Our routing protocols support that. However, it is far better and more efficient for our network resources if we can summarize those into one or maybe a couple supernets and advertise those upstream to the core. So C, D, and F, those are our answers. Well, you could probably have guessed that this was coming. Which of these services are associated with the core layer? Now, if you're paying attention and using process of elimination, you might have noticed that B is the only service that we have yet to use. And indeed, that is actually the only answer here. We're not focused on features at the core layer. We care about one thing, and that is very quickly switching at a layer 3 perspective among network locations. So in this case, B is our only answer. Last question. Which network blocks are eligible to be collapsed together in network design? And again, choose all that apply. Well, if we're going to choose all that apply, then we're going to do something like this. Circle all of them, because we can collapse any network block into any network block. We talked about collapsing the core into the distribution block and the distribution to the access. Hey, we could take the aggregation block and collapse that back into the core, or take the internet block and collapse that into a distribution layer. Remember, this concept of collapsing is essentially taking 2 different network blocks and adding them together. So regardless of what number 1 and number 2 is, we bring those services together into a single set of hardware. The hierarchical network model is fantastic for scaling all the way up to the largest enterprise networks, but also helps us scale down into the smallest networks. And the way we do that is primarily via collapsing. Well, that wraps up this quiz. If you find yourself with any gaps in your knowledge, be sure to go back and watch the appropriate videos in order to fill those. Otherwise, congratulations on completing Explain the Hierarchical Network Model. I hope this has been informative for you, and I'd like to thank you for viewing. Welcome to Explain the Hierarchical Network Model. If we're going to be building and designing layer 2 and layer 3 networks, then we need to have some foundational concepts as far as how we put these networks together. And what we're going to find is this hierarchical network model feels a little bit like building blocks, like putting one block onto another block to build a tower, or in this case, a network. In this video series, we'll be exploring all of the different network blocks that make up this hierarchical model, including, by the way, the access layer and the core layer and the distribution layer, and these layers that we're used to talking about, but seeing it more holistically, zooming out and seeing it from the big picture perspective. So come along as we explore the different elements of the hierarchical network model. And with that, I will see you in the next video. Pause for a moment to think about all the different ways we leverage modularity in the networking world. We have the OSI model where we can swap different components out at different layers. For example, swapping out a fiber cable for a copper cable and nothing else changes. Same with a chassis switch. Cisco makes chassis switches and we might buy that switch with a bunch of copper ports and then we find out we need fiber ports down the road. And so we pull a copper port out or a copper module out and we put the fiber module in. And the whole purpose of modularity is to future-proof us, to make sure that, okay, we don't exactly know what's going to happen down the line, so we're going to build it like this. And then if something changes, we can swap out the modules or swap out the components that are needed in order to make it work for the future set of requirements. Well, the same thing happens with design. We don't want to design our networks so that they're rigid and they can't become flexible when we need them to change with our business needs. Because we don't know what our business is going to need one day. And one of the best ways that we can build flexibility into our network designs is by leveraging modularity. In this video, we're going to discover that the hierarchical network model is going to give us that modularity. Let's dive in. The goal of the hierarchical network model is to aggregate parts of our network into components that we would call building blocks. These building blocks are all going to be attached to each other at layer 3. Additionally, inside each block is going to consist of some number of network devices. In some cases, those will be routers. In some cases, those will be switches. And in most every case, we're going to have at least 2 devices in each block. Now, when we draw a logical connection like this to show that 2 blocks are connected at layer 3, what that actually means from a physical perspective is we might have a full mesh of connection among some edge devices in each block. And the idea here is that we continue to scale our network architecture out by adding 1 block at a time. So maybe something like this where we add 3 more blocks on the right and 3 more blocks on the left. And what each one of these blocks is doing, well, it's going to depend on what we want that block to do. We have a lot of different types of blocks that we can deploy into the network, and probably the most important type of block that we can deploy is going to be the core block. In the very middle of our network is going to be a block whose primary purpose is to connect all the other blocks. When we talk about a true network core, this is what we're talking about. We're saying that all traffic must go through the core from one block in order to get to any other block in the network. Now, as for the rest of these other blocks, we could have blocks that are aligned to a physical location, so we could have multiple buildings represented by these blocks, or we could separate these blocks by logical function. Let's say that we have a headquarters building, and that headquarters building is going to have a distribution layer. The purpose of the distribution layer is to connect to the core layer at layer 3, and then to connect downstream to all the access switches that connect our users. As such, in this case, we're actually going to hang another block off of that distribution layer. And this would be an access layer block. Again, we draw one logical connection, but if we have 15 different network closets, then that might be 15 or even 30 different connections going back to the distribution layer. So that's our first building. We have a headquarters, but then let's say we have a second building. Maybe it's a branch office with its own set of distribution switches and its own set of access switches. One of the advantages of having a modular model is the fact that we can copy and paste a concept like a distribution block and an access block and use it as many times as needed. For example, we might even have a third building over here with yet another distribution block and yet another access block. And we can have as many of these as we need in our network in order to build it out. This is a far superior way of scaling out our network as it grows, because if we don't know where we're going to connect things, we might just end up with haphazard connections among some of our buildings. For example, we might have a distribution switch that pops up at a new building, and because we don't really know how to scale out a network, maybe we connect that into a different building's distribution switch, or, oh man, heaven forbid, we should connect that into an access layer switch at a different location. No, instead what we're going to do is we're going to modularly scale out this network regardless of how many building blocks we need in order to make that happen. And this increases the importance of the core because now the core is responsible for connecting every part of our network. We don't just hang distribution switches off of distribution switches anymore. We are going through a dedicated core in a lot of cases. Now there is a concept of collapsed core, and we will be getting into that later on in this skill. But even with a collapsed core environment, these same principles apply, and so it's important that we start here, assuming we have a true core layer, and then from there we can explore collapsed models. So what are some of these other networking blocks that we might deploy into our network? Well, first of all, we might have an internet block. The internet block in a lot of cases is going to have the internet coming into it, and then we might have a DMZ, we might have the firewalls in here. It gives us a part of our network that is layer 3 attached that enables us to swap components out, or maybe even have 2 internet blocks if we have multiple internet circuits. Now another option might be the WAN block. This would be a set of switches that are dedicated towards connecting all of our remote locations that are connected through the wide area network. We might also have a network services block. The network services block is sort of a catch-all block that's going to have a lot of services in it, such as wireless LAN controllers and load balancers. Potentially even firewalls could go into this if they're not in the internet block. Furthermore, we might have a data center aggregation block. A data center aggregation block is essentially another distribution block that actually connects to a data center access block. But we flag that as a unique block because there are a lot of services that are needed inside a data center that are not required outside of it. And so when we talk about an aggregation block, instantly network technicians were supposed to know that, oh, we're talking about the data center now. So we're going to expect technologies like fiber channel over Ethernet and virtual port channels and such. So as we continue to scale out this network, we see that this is actually pretty simple to do. If I need a new network block, whatever that is, whether it's a distribution or an aggregation or an internet block or a WAN block, regardless, I do the exact same thing. I connect it into the core at layer 3, and I build it out as I need within that block. Furthermore, this keeps my network robust, because as I scale out my network, well, there's more likely to be a problem one day because I've just got so many network nodes out there. So let's say in this building down here, I all of a sudden have a broadcast storm one day. Well, because I made this a layer 3 link, the broadcast storm is going to be isolated to that location. So I don't need to worry about that broadcast storm affecting every other network block in my domain. Ultimately, the hierarchical network model is going to be the foundation for how we build real-world networks. It's not always going to map perfectly to what we've drawn here, but at the same time, it gives us a starting place, something to build on as we start figuring out how best to build a network for our organizations. So as we look at the hierarchical network model, what we see here is that we are less concerned about how to connect all of the switches and routers and networking components to each other, and more zooming out high level, seeing how the different parts of the network all connect to one another. This is a building block model. We're concerned with the blocks and how to add new blocks and how to swap blocks out depending on the scenario. Now, when we look at the block right there in the middle, the core block is going to be one of the most important blocks of all. And again, we're going to talk about how we might collapse that into a different block, but foundationally, we need to understand that all of the other blocks in the network are going to hang off of the core, with the only exception being access layer blocks, which hang off of their respective distribution blocks. Last but not least, the advantage of deploying the hierarchical network design, we talked about a few of them. We talked about scalability, we talked about robustness, fault tolerance. It can be cheaper to deploy the network this way when we have a plan in place that prevents us from purchasing something that isn't going to actually help us in the future. So giving us this flexibility with adapting to changing business needs is another big advantage of the hierarchical network design. So overall, this is absolutely where we're going to start anytime we're talking about designing and building a new network. I hope this has been informative for you. I'd like to thank you for viewing.